So welcome everybody. I'm Dakota Stranik with the Whatcom Conservation District. I'm a dairy planner and resource specialist there. So I work exclusively with dairies. I do farm plans and I also help with cost share projects. So if you're interested in any of that, please come talk to me. And my business card is over on the table as well. So you're probably well familiar with Whatcom Conservation District and the resources that we offer to landowners in Whatcom County, trying to facilitate your decisions and help your decisions as you're making them around water quality and land use. So you're the landowner, you make the decisions, and we're here for a resource to give you information as you make those choices.
Hi, my name is Scarlett. I also work for the Whatcom Conservation District. And my job there is to set up small research studies on farmers' fields and try to collect data on how well best management practices work here locally. And so I'm going to be telling you about one of those studies related to irrigation here today.
Hi, I'm Wallace, co-founder of Coda Farm Technologies. I grew up in the Skagit Valley, just south of here on Wallace Farms.
Then I'm Troy Peters. I'm an extension irrigation specialist, an irrigation engineer, and a professor at Washington State University. And I do everything related to irrigation, any agriculture and water. That's kind of what I try to specialize in. And here to talk about just some basics of irrigation management, and then to answer your questions. And then, yeah, please call me, and if you have any questions, we can work out some things.
So I passed you guys some of this sheet out to you guys with the water level control structures, and so this is just an overview of what I'm going to be sharing with you. And so the project that we've been working on at the Conservation District that's funded by NRCS revolves around SUB-IRRIGATION. And so that's a technology where you are trying to raise the water level to irrigate your plants from below and laterally through capillary action. And so many of you guys know up in Whatcom County and also in Skagit, our farm fields are drained through both drainage ditches as well as drain tiles. And this is very beneficial in the winter and the springtime to move water off the fields. I'm sure this spring everybody wished that it was being a little bit more beneficial because it's been a very wet spring. But in general, these drainage systems are helping farmers get out into the fields earlier to take their first cutting, to make nutrient applications, to make their plantings. But eventually we're going to get to the summertime, and it's not going to be raining as much, and those drainage systems are going to be continuing to drain our fields, and at that point it can become detrimental to your crop yields and can also become an inefficient use of the rain that's falling if we continue to drain these fields instead of keeping it in the soil for crops. And so the idea of sub-irrigation using these water level control structures is that you can have the fields be draining all winter and spring, and then in the spring, after you've got out there, done your first field work, you can control the drainage using these control structures and actually hold the water back from draining from your fields. And there's several of these deployed here in Whatcom County already. And so our study is trying to take a closer look at how much of an effect this controlled drainage can have on a field. So for example, if you have a ditch or a drain tile, we want to try to learn how far away from that drain tile can you see an effect from sub-irrigation. So that's kind of like the questions that we're getting at with this study. And the main water level control structure that we have been using is by a brand called AgriDrain. And there are these commercially available structures. They cost between $600 to like $1,500, so they're fairly affordable structures, and they're big and tall, and you buy them based on the depth of your drain tiles or your drainage ditch, and you dig down and you put these in line with your drain tiles or your ditch, and whenever they're totally open, water just passes through like it's a normal drain tile. But whenever you want to start to hold the water back, you can put in these baffles or stop logs, and they will they kind of get taller and taller, and so upstream of that water level control structure, you can theoretically raise up the water table enough to have your plants be able to reach water. And another thing you can do to even supplement this is to actually add water back to your system into a drainage ditch and try to hold that water back that way. So in this way, you can both make better use of the rainfall and potentially make better use of irrigation water by just kind of adding it to the ditch and holding it back into your field. So we have two of these we have two like small studies set up here in Whatcom County, trying to get numbers on how well these things work. Ideal sites are sites that are flat, which is most of our farmland around here. Sites that have very well-known tile drainage as well as drainage ditches. The tile drainage piece is definitely like a complicating factor out here. It's not always totally known where the drain tiles are, and so that's been something we've been learning, is that one, locating exactly where those are, and two, flushing them out is something that we kind of learned during our first year of study. In fact, there was like an unknown drain tile that kind of connected our upstream and downstream fields and funneled water around it. So yeah, getting a better sense of where these drain tiles are is something that is important to our study. And so the potential benefits of using these water level control structures are that it could improve your yield on your field, as well as require less overhead irrigation work. You're going to maximize the use of the rainfall that's already falling, as well as overhead irrigation, because it's going to be holding that water back from draining out of your fields. Finally, there is potentially water quality benefits from using these. If you have less kind of drainage seeping through your field, you can have less like nutrients leaching, less potential issues from manure getting down like a crack in the field that's going to a drain tile. And so there's these other added benefits too. If you're interested in learning more about these, we are actively collecting data here in Whatcom County to try to get some data behind, like, yes, this is something that works well here and that you could kind of like retrofit into a system that you already have.
Hi, I'm Connor Wallace from Coda Farm Technologies, and I wanted to talk today about hose and reel irrigation. Just by show of hands, has everybody seen irrigation like this before? Or has anybody not seen irrigation like this before? Looks like people are pretty much familiar with it. Let me just give you a little overview about how it works. So these are mobile systems. You can bring them to any field that has a water source. The way that they work is that gun cart's towed out into the middle of the field, and then it's pulled back in over a period of about 10 hours. And it's irrigating like around 300 gallons per minute. And what's nice about these systems is that they're totally portable. So I can hook up some hose to, I think this one will be like supplied by a pump that's maybe a half a mile away. And I can irrigate this entire field even though there's no permanent infrastructure. So that's really nice for a lot of reasons. It helps a lot of crops like the one that, farms like the one I grew up on, Wallace Farms. We don't have any permanent infrastructure. We just have a bunch of fields around in the area that we go and we irrigate. I want to talk to you a little bit about automation that you can do on these and how you can improve and make these a little bit better, because they have a few different trade-offs. Obviously, one of the benefits is mobility, but with that, you also get one of the cons, which is you don't really know what these are doing at any given time. In fact, they move so slowly that you have to be right up against them to actually see them moving. It's kind of incredible. Along with that, you'll also have crews of guys that will, go around and move these around. And so as a farm manager, you may not even know where one of these devices is. One of the worst parts about working with this kind of irrigation is that these will run for like 10 hours. And in the middle of a run, it may stop for some reason. Let's say that one's run by an actual like gas lawnmower engine. So it might run out of gas, or it might stop for some reason. Maybe it comes out of gear. And that means that this irrigation reel will flood that field for until you come and take a look at it. So a typical one might be like you set it out in the middle of the night, you say, okay, it's going to come in at around 5 o'clock in the morning, and then let's say at 1 o'clock it stops. So you can imagine half an acre out there just being completely inundated with water. Obviously not great for a lot of different reasons, but you're going to ruin half an acre of crop. The other thing about these that's really frustrating is record keeping. So as you can imagine, there's lots of different crews out going and doing different things, and you're having to move these every 10 to 12 hours to get a full usage of them. So, you know, record keeping is really difficult for a farm manager. So with all that in consideration, let me tell you a little bit about the solution that my brother and I came up with. When we came back to the family farm, Wallace Farms, my dad asked us if we could make something that would help deal with these issues, because we rely on these systems, but they just have so many drawbacks that it's difficult to work with them. In fact, it's one of the worst jobs for our family farm. So we made a device that's a universal retrofit that goes on any pump and any reel that will allow, when this reel stops for any reason, it can shut off that paired pump. So that is automatically keeping you from having those flood events. But you also get an app that has real-time data, so you can see exactly where these guys are at. It gives you record keeping, so you know which swaths that you've done. And it also lets you know, you can control it from any place in the world. So, you can be in Hawaii or something and turn off your pump, which is kind of fun. And so the other really nice thing about a device like this is that it gives you application rate data. So one of the frustrating things is like, I don't know if you all know the bathroom timers that you use when you go in the shower, but when the farmers use those exact same timers for the pumps that they hook these up to. So what's the first thing that you do when you go into the shower and you want to turn that timer? You crank it much higher than you need to. So that means that when these get done, they usually run for a good 30 minutes afterwards, just because you don't want it to turn off the water before it comes in. So our device cuts down on that kind of waste quite a bit. I can tell you a bunch of different factors about like one of the reasons why you might want something like this. We found that we got an 8% water reduction of gross water usage. We also found that 1 in 20 runs of these fail. So a pair of these devices pays for itself basically in the first year, basically pretty quickly. And it's also just for peace of mind too. When my brother and I founded this company, we just basically wanted to help out farms like my family farm. And one of the biggest stressors is having to wake up in the middle of the night or not knowing what's going on.
The idea with irrigation, right, is we have plants that are using water, and we want to apply, we don't want to do work that is unnecessary, and we also don't want the crops to experience water stress, right? When it dries out in the middle of the summer, we lose yield, and so we don't want that. The other thing that happens is, soil, water's a polar molecule. So you have the two hydrogen on the one side of the oxygen atom, and so it gives that, it gives it a positive side and a negative side to that H2O molecule. And what that means is that water molecules like to stick together. And so it's kind of stuck to the other molecules next to it. And so if I stick my finger in there, that's why the molecule is sticking to my finger, and then it's also sticking to the other water molecules next to it, so that it kind of creates a drip together, and that's why water coalesces into drops and then gets so heavy that it falls out of the sky and all this other. So water likes to stick to things, and it likes to stick to other things, but that connection is weak, and such that, when it gets too heavy, then gravity takes over, and then it falls off as a drop. So this is how soil holds water, is that the water is sticking to the soil particles, and then it's pulling its buddy molecules in behind it, so that that allows soil to hold on to water. But there's a limit, obviously, to how much water that soil can hold. So right now it's holding more and more water, but at some point, if I put water on there that the soil can't hold, from the top, it looks good, right? It's going into the soil. I feel good about this, but it will eventually go out of the bottom of the profile. If there's good drainage, if there's somewhere for that water to go, it's going to go down and go into the groundwater. If there's nowhere for that water to go, if the water table's high, it's just going to build up the water table in the field. And this is what we are talking about here, is using these drainage structures to control that water table in the field as a method of irrigation. But in some areas where you don't have a high water table, and you have good drainage, then that water will be lost out of the bottom of the profile. The other thing to remember is we're putting nutrients. We pay money, right? Even if we're using dairy manure and spreading it out there, it costs us money to get those nutrients out onto the field. And we want the maximum use out of those nutrients that we can get. And when those nutrients, they're going to stay in the soil, except they're going to move. The only way they can move out of the soil is either when you haul it off of the field by harvesting it and hauling it off of there, or it's going to move with the water, right? Or it volatilizes and goes into the air. But a large source of water loss in a field is that it gets dissolved into the water, and then it moves, and then we put too much water on, and those nutrients get lost out of the bottom of the profile. And so we lose the benefit from those nutrients. So we want to do good irrigation scheduling. So right now, when the soil is really full of water, I just a little bit of squeezing, and I get a lot of water out of it, right? So when the soil, the maximum amount of water that this soil can hold long-term against that pull of gravity is called field capacity. And so that's a full soil. And when the soil is at or near field capacity, the crops have very little problem getting all the water they want out of that. However, after a while, it drains down to where there's still water left in the soil, but then the plants have got to, they're pulling on it. It's that water molecule stuck to that soil particle, and it's pulling its buddies away, and then the roots have got to try to pull that water away from the where it's stuck onto the soil, and it becomes this battle, and the plants start to lose after a while. As it gets drier and drier and drier, then the yields start coming down. There's little stomates, little holes in the leaves that exchange carbon dioxide in order for photosynthesis to happen, but it loses water vapor out of these stomates. And so when plants, almost all plants have this self-defense mechanism to where when they're not getting as much water as they'd like, they close those stomates so that they don't lose water at the same rate, because if they keep using water at the same rate, they're going to die. And no plant wants to die, right? And so it closes those stomates, and when that happens, the water use rate decreases, but it also decreases the photosynthesis rate, and you have yield reductions associated with that. So that's not something we want to do. So we want to be able to irrigate in a way that we are putting just enough water on there that soil holds it, and the soil is at or near field capacity or slightly below. And then we don't get into that water content where it's starting to fight with the soil. And when that happens, we see water yield loss. If it's really sunny out, if the wind is dry, if there's lots of wind, then your crops are going to be using more water than if it's overcast, if it's a little drizzly, the air is very humid, and there's very little wind. And so what we do is we've put together a model that models the crop water use rate, or we call it evapotranspiration, or ET. So evaporation plus transpiration, that's the amount of water that the crop is being evaporated up out of your fields on any given day. So we can model that, and we've put it in an app. We have weather stations located around this valley, and we are measuring that weather data, and then we model it, and then there's a tool that we put in here. And so you just say, okay, here's my field. I put, I ran the hose reel out, and I put on 1 inch of water, and so on this date, and then it says, okay, you put on an inch of water, but yesterday it uses 1/10 of an inch. Next day it uses, you know, 15/100ths of an inch or something like that. And it decrements how much water is in the soil, so you can get an estimate of about when your crop is going to start to begin to experience water stress, and you can irrigate at that time. And then the other thing is, if I'm putting on an inch and there's only 1/2 inch of space in the soil, that tells you, hey, take a break, you know, give it another 5 days before you run that reel out and irrigate again. So it can give you an idea of when you can irrigate and how much water. So the way that this app works is it keeps track of what's called the soil water deficit, or field capacity is full, how far down you are from full, which gives you the amount of space that's in the soil for you to apply additional water, so that you can have an idea of when to irrigate and how much water to apply. So that is one tool that we can use to do irrigation scheduling, this is the Irrigation Scheduler mobile app that hopefully you can use on your phone. We used to be able to download it from iTunes or Google Play, but we've had some problems with that lately, but you can still use it. You just use it as a website. So you navigate to the web location. So on your phone, you open up Google Chrome or Opera or whatever you use on your phone for a web browser. You type in this address, and then you go up to the 3 dots and you say, put a link to that on my home screen, and it'll pop up on your home screen. And from then on, you won't be able to tell that it's not an app, because you click on that icon on your home screen. It's going to open it up into that web browser, but it's going to look and behave exactly like an app. And it's going to remember who you are, you know, your username and password. It's going to bring up your fields. You can put as many fields on there as you want. In this type of case where let's say we've got a reel and we're irrigating here next day and we're moving on down through the field, how do I irrigate that? Because it's irrigating different parts of the field at different times. Well, what we usually tell people is just pick the first spot, and then that'll tell you when to fire it up, and then irrigate, and then it'll give you an idea of how long to wait before you need to hit that, to turn it back on and put the reel, start over in that same spot with that same hose and reel. The other way, so one spot is doing irrigation scheduling using weather-based data. It's a model, right? And models all depend on, you know, what garbage in, garbage out. And so definitely go into that app, and there's something called field settings. And then we estimate about, let's say you're growing corn. We estimate what the starting growth date is based on long-term historical averages and stuff, but every year is different. You guys do whatever you need to do for different reasons, so those dates are going to be not quite accurate, and I encourage you to change those dates and then just play with those settings a little bit so that it represents your field a little bit more closely. The other thing that we do for irrigation scheduling is we can measure of water that's in this soil. We can get an estimate. So there's 2 things that we can measure. We can either measure the soil water tension, or how hard the soil is gripping onto those soil particles. So as it dries out, it pulls and pulls and pulls a little bit harder and harder and harder until and then we can measure that soil water tension. The other thing that we can measure is soil water content, or the volume of water that's in this soil. So soil obviously is this 3-dimensional structure, and then we have root depth down here. Usually that is usually measured as a percent of the total volume. So let's say it'll give you a number like 25%. So that means the 25% of this soil volume is water. There's obviously, soil is composed of little bits of rock, and then, you know, bits of organic matter and stuff, but it's mostly little bits of rock, and that takes up most of the volume. So the maximum amount of water you can usually get in most soils is like 40%. But if that 20% number, that's the other thing that we need to do. So let's say my soil water volume is 20%. we need a depth. We need to turn that into an inches of water that we need to apply, right? And so all you do is you multiply that by the depth of the root zone that you're managing. So 20%, and we're managing, let's say a 1 foot deep root zone, or let's say it's 2 feet deep root zone. So 20%, we multiply by 24 inches. 24 inches times 0.2, and that's going to give us what, 0.48. So 0.48 is the volume of water in inches that is in that soil profile. And then you compare that to what your field capacity is, and then we've put some tools together to give you an estimate of what field capacity should be for any particular soil. That's on irrigation.wsu.edu, to give you a starting point as to what some values are based on soil texture, but you can kind of refine that over time. So the difference between the volume of water in your soil versus where it is at full, that'll give you an idea of how much water you should put on in any given day using soil moisture sensors. So that's volume soil moisture sensors that measure the volume, but the soil water tension, those are much easier, because if the soil water tension is 0 or very close to 0, it's full. And as that soil water tension gets higher and higher, it means it's drying down, and you just draw a line, say, okay, I'm going to refill it when it's at 30 centibars. This particular one is a soil water tension sensor. So this one you would bury in the ground at a particular depth, and then you plug it into a data logger, and we have one set up over here that you can use, and that'll give you the soil water tension. And so a bar of pressure is 1 unit of pressure. So you can convert between bars and PSI and pascals and Newton meter squared. These are all units of pressure, but they use bar, and 1/100th of a bar is a centibar, and so we measure centibars as a unit of that tension. So the other way we can do it is with, and so this, if I plug this into this sensor, it will go in just like this, and then you can see it's got AA batteries, and it's got these are rechargeable, and it's got a solar panel here, and this has a cell phone modem integrated into it. You put a T-post in the field out there, and you tie this to a T-post or whatever you want to do, and then this talks to through the cell phone network. It stores that number on the cloud. You just log on to a particular website, and it's going to give you that data. In fact, we had it set up so that it can work right now, where she was able to plug it in, and then she gets on her iPad, or you can also do it on your phone, and you can see what number that's measuring at any given time. So for these types of sensors, this is a soil water tension sensor. A good number is like anywhere from 30 to 60 centibars is where you want to irrigate before it gets to 30 to 60 centibars. We also have some publications, again, irrigation.wsu.edu, to show you kind of how to use these sensors, compare them, practical use of them, etc. This one here is also a soil water tension sensor. This one is a manual one. It does not connect. You have to go out and read it manually, but you would fill this, it's just basically a tube that you would fill with water. And this one's broken, but I'm glad that it's broken, because it shows us what's inside of it. And you can see this is like a porous ceramic cup, and inside of there it allows the water to come down in here, and the water, these pores in this ceramic are so small, the water can move very slowly in and out of this, but you can't get, if it's wet, you can't get air bubbles in here no matter what the tension is. So we bury this, and this one I took the gauge, but this one is missing the gauge. and they're different lengths because we want to measure it at different depths, right? So we put that in contact with the soil. The soil pulls the water out of there as it dries down. And if you irrigate, water moves back in because the tension in here pulls that water back in, and we can measure that tension directly with a vacuum gauge. That's all this is a vacuum gauge, and it's measuring what the soil water tension is. But here's an electronic version of the same type of sensor. It measures that soil water tension. You can see that it's basically measuring the resistance between those two plates. The more water that's in the soil, the less resistance you have between those two plates. This is measuring the capacitance of the soil, or that the soil's ability to temporarily hold an electric charge, which is a function of the soil water volume. The longer it is, the better it is, because it's measuring a larger volume of soil. And one of the biggest problems with these types of sensors is that it's very sensitive to what's happening immediately next to the sensor, like within millimeters, which means that installing these is pretty important, installing them properly. So you've got to sense it in, push it in there. And that's why the longer it is, the better it is, because it's integrating across this larger volume of soil. The reasons it's short is because people want to put them in at very deep depths, and they don't want to have to excavate this huge hole. And so they just auger a hole about this big, and then they insert it into the side of the hole is why. So the question is whether there's sensors that measure the moisture in the plants themselves. And the answer is yes. There's something called a pressure bomb. And basically, this is a manual measurement. You go and you cut a leaf off, and then you put it inside of this pressure chamber, and you seal it around the stem of that leaf as it's sticking out. Then you increase the pressure inside of that chamber until water starts coming backwards out of the leaf. And then you say, okay, that's the pressure that was inside of that leaf that caused that to go back out. And it measures what's called leaf water potential. It's fairly time intensive, and it's not very, you can't automate it. Like, the cool thing about this is you can wake up in the morning and check it on your phone, and it's there. And that you have to kind of go out. And so people that use pressure bombs are usually like orchard and vineyard managers and things like this. Not many field crop. The other thing with field crops is they have tender stems, and you put them inside of that and it crushes the stem, and it just doesn't work as well. The other thing that I've done a lot of research on is actually detecting canopy temperature. And so as the stomates close, then it's not evaporating as much water out of the leaves. There's not as much transpiration, and so the leaves warm up a little bit. They're a little warmer than what they should be given the weather conditions. And so if we say, okay, given the weather conditions, this is what the temperature should be if it's fully transpiring, and then we use infrared sensors, temperature sensors, to measure what the temperature actually is, then we can say, okay, there's a difference of this. But unfortunately, it's not very precise. That's actually what they are doing right now with satellite-based imagery, is they are using satellites to measure the temperature of your fields. And then they also can use satellites to measure using the reflectance of various spectra across the entire multispectral bands, near infrared and ultraviolet and everything. And then they can get an estimate of how green and how leafy that particular field is, and then based on that, about how water stressed it was compared to what it should be. And then they're using that as again, it's a rough estimate of about how much water is being used by your field at any particular time. And they do it in a spatial manner. Unfortunately, the thing with satellites is it gets like a 30 meter by 30 meter pixel size, which means it's on a very large scale. Really quickly regarding the big gun and the reel, maybe some of you guys have seen boom carts. Big guns, they operate at really high pressure because they've got to throw a lot of water a really far distance from it. And so whenever you have pressure, then it's more expensive. It's more expensive to pressurize water up to 110 psi than it is to pressurize water up to 30 psi, and so it's a little more expensive to run a big big gun than it is to run a boom cart. So a boom cart is basically the same idea, and it runs off of these reels, but it has these two arms that are cantilevered out the side of it, and it's still on a cart, but it's got drops, sprinklers that come off along these arms, and then those sprinklers operates pretty much like a center pivot, basically, and then it pulls in and it's irrigating underneath there. It's much more efficient. You get more of the water that you're pumping to the ground. You have less loss to wind drift and evaporation. And especially, everybody knows with a wind gun, with a big gun on a windy day, it just, your pattern, you want it to be here, but it's heading off somewhere else. It's kind of a pain. But the big, these boom carts, they're better at putting the water where you want it. It doesn't get distorted by the wind. And then also, because it's not as affected by the wind, it's much more efficient. You get about 80% of the water to the ground versus about 60% of the water to the ground with a big gun. People mostly are doing it for quality reasons. Crop quality, especially on higher value crops like potatoes and vegetables, where that distortion by the wind, where you have this big strip that just didn't get irrigated right, or you got too much water and some not enough, so you have some potatoes really big and some that are scrawny, that can be really expensive in terms of quality return to the grower. And so that boom cart gets the right amount of water to the ground, and they're making more money in terms of crop quality.
Put it on the end of the hose and take the gun away?
Yes, that's right. It's a cart. You use the same reel, you just use a different cart. It's a little bit more expensive. We need a local manufacturer actually to start making these things, because right now I think they're having to get them out of Europe, and
Europe or England.
Yeah, so that's kind of a pain. This tool is built on top of and in collaboration with AgWeatherNet, and it uses AgWeatherNet data. It also uses other network data, but the number that it actually calculates is reference evapotranspiration, which is the amount of water that a full-grown alfalfa crop would be using if that alfalfa crop was out on any particular day. And that number gets multiplied by a crop coefficient that's specific to that crop and that crop's growth stage. So here we have some, looks like corn that's just barely popping up. The crop coefficient is very tiny. This has been, it's green, it's growing, it's using more water than that is over there. And so the crop coefficient would be different for this field than it is for that. But the number you get from AgWeatherNet is reference evapotranspiration. So, and that's why I was talking about the dates are important, is because we're trying to figure out what the crop coefficient is for your particular field. And that depends on your crop and the crop's growth stage. And then honestly, some of that is just kind of like this, because, and so we have ways in there to adjust those crop coefficients up or down. Let's say it tells you to put on water, and you go out there and you're like, no, that's wrong. There's a lot of water out here. So you go into the model and then you adjust that down, and it can be wrong for a lot of different reasons. The slope of your field, the variety of crop that you're using. Sweet corn is going to be different than field corn. Your planting density, there's all kinds of things that's going to make it so it'll be a little bit different. And we don't know that stuff, and there's really no way for us to know that stuff. And so we just allow you, there's a button in there that says adjust it up, adjust it down 5%, and then it'll just do it that way. So I just had one other thing. So especially with these big guns, let's say it throws 80 feet out this way and the other 80 feet. So the temptation is to the next set is 160 feet from where it was before, right? Because it throws 80 feet. We want to go to the 80 feet. What happens though in reality is that results in kind of poor irrigation uniformity. And so if you do it that way, just something to consider is the next set, put it in between. You know, in other words, so let's say I set here, and then next time I set here, well, the next time put it here. You know what I mean? Split the difference between where it was before, and that'll help fill in those spots that you kind of missed. And then it'll put less water in those areas that maybe you got a little extra last time. So just something to think about to improve your uniformity, and you'll get better yield everywhere with that type of a system.
Another thing that we wanted to talk about that I'm hoping Bart might be able to mention is pressure testing your buried pipelines. So it's kind of out of sight, out of mind for many producers, is if these pipelines that are underground, but if connections break, then that can cause a world of hurt for you, and especially if you're using those pipelines for manure transportation and something maybe gets into a waterway or a ditch nearby you. That's definitely something that I know all of you want to avoid, and so pressure testing is an easy way for you to just do some management every year when you have the time. You can pressure test and make sure everything's good to go, and that way when you're in the season doing your manure application or your irrigation, you're pretty confident that you're not going to have any problems.
What we do is we have a 10-foot tall piece of 8-inch pipe, and it's got a ring lock fitting on the bottom to fit on top of our risers. And we'll pick the highest point on a section of line that we're trying to test, and first we'll flush that line with water, and then we'll fill the pipe with water. It's got a clear sight glass on the side, measured with marks on it every foot, and there's a formula that they have that you use for the length of pipe and the size of pipe to determine how much leak you're allowed to have in that 10-foot tall stand pipe. And so it's within a 2-hour period that you just measure your loss, and whether if it's in the acceptable range for, yep, that's pretty much it, I guess.
Great. And so how many times do you have to do that, or how many fields, like how long would it take you to do that? Can you do it in a day for all your fields, or? For
a section of line, you can do it in a day. It takes a little time to set things up, and then for flushing lines and everything, making sure there's no air pockets, and yeah, just yeah.
And the cost would pretty much just be your labor
time.
And maybe some pump time?
Yeah.
Okay.
Yeah, so basically it's just a leak down test. It's really, I mean, not really a pressure test per se. It is putting head pressure on the line, but it's just checking for leaks.
And what time of year do you tend to do that?
In the late winter, just before we go to use the pipeline again.